Okay, let's continue. So, after we have been looking at the consistency, we want to address now stability. So we can give a general definition of stability. A finite difference method, partial differential equation, is called stable if we can choose some norm here. Choose, for example, the 2 norm of the finite difference method solution. So then that is a vector. Try to indicate that by a little bold u at the time level. It should be a bold un, but it is our vector of unknowns, our approximations at the grid points, say from x0 to xnj. If that stays bounded, for any time level n. So, and we can express that also in a more concrete, more mathematical way. If we limit ourselves to an initial value problem, so in S, that means what the stability means for an initial value problem. That is a PDE with an initial condition. And it's going to write it in the way that we say u of x0, so this means time 0, is equal to some given function f of x. So the f is then our initial condition. So for an initial value problem with initial condition u equal to f of x, this FDM solution should satisfy u, the bold un satisfies following. That is 25. Now, I'll give a definition in a minute, that this 2 norm of the numerical solution can be bounded by some constant times e to the alpha tn times the 2 norm of the initial condition. Don't be worried, we take that much easier in a minute. This is just the definition where k and alpha are constants. Independent of the initial condition f, grid spacing delta x, and time step delta t. And usually the alpha is 0. But the definition is general that we can allow even for exponential growth. Usually alpha is 0. So for our examples, usually alpha 0. If alpha is 0, e to the 0 is 1, so then it just means that the solution at any time level is bounded by the initial condition. And that is what stability means, continuous dependence on the data. In that case, the data are the initial condition. If you would have boundary conditions, then also they would also be involved here. But we limit ourselves to that. And the 2 norm, that is the following. That is something useful when you do the check of the accuracy to compare the numerical solution of a PDE with the exact solution. Then it is useful to use this 2 norm. You can use also others, but that is quite a useful one. So the 2 norm, and that is also called standard. The mathematicians would call it standard L2 norm. So that is space can do it, but for us just the 2 norm is defined by following. We say the norm of u, if we take it n, we have that to indicate. It means that we have to take the grid spacing delta x and multiply it by our values, and usually here we assume that we have periodic boundary conditions, so that the j equals 0 is the same value as at nj. Otherwise you would also include the 0, that is not a problem. Then we take our numerical solutions, ujn, which approximate the exact solution at the grid point xj, time level tn. We take those to the power 2. So we take these, our numerical solution, we square that and sum, and take the square root of that. You could also, yeah, that is the definition. That can be easily computed, and especially interesting is it when we look at the error. When you have the exact solution, and we have then when we want to compute un minus u exact, then we would compute this numerical solution minus the exact solution, u of xjtn. Square that difference, sum it, and multiply the delta x and take the square. Then we have a measure. In that case here we have a measure of the solution. Otherwise, what I just said with the error, we have a measure of the error. But here it is said that the solution, the measure of numerical solution then, should be bounded by the corresponding measure of the initial condition. Why is this interesting? Because this is approximating the integral. If you look at that, if you think of it as the midpoint rule, then you'll see that the 2 norm of the numerical solution, un, that is approximating the integral. If we take that squared, then we see it immediately, then we get rid of that. If we square it, that is the integral of u xt n to the power 2, and we integrate over x. So that's the integral. If we had 1/2, then it would be really the energy that we had in the system. That is then, well, that's so. That is a. So that is has some physical meaning actually. So this is all a little bit abstract, and we will cut that down to more basics by looking at a concrete way to do this stability analysis. There are a couple of ways, and we shall learn the most important one. That is the so-called von Neumann stability analysis. That is named after John von Neumann. I showed his picture in the very beginning, who found out the importance of doing this analysis. There are other methods. One is called the energy method, which is very much based on these 2 norm, and that we can estimate the energy of our PDE. That's really the physical meaning of energy. We can also estimate the corresponding discrete energy. And there is also a method, normal mode analysis, also Gustafsson Kreis-Sundström theory, which involves Laplace transforms. These other theories, the mode transform, normal mode theory, and energy method, they are too complicated. I teach the energy method in a PhD course. But the von Neumann analysis, that is something that you should know. And it's, although it is limited in the application, it is extremely useful also for cases where the prerequisites are not fulfilled. So now we look at this von for Neumann stability analysis, and first we shall state the prerequisites when it can be used, but I add immediately you can use it even outside and get some good hints. So we shall consider now the for Neumann stability analysis. This is also called Fourier analysis. You will see in a minute why Fourier. First, the prerequisites. The finite difference method should be linear. Of course, when we are relying here, we should see on Fourier modes, and there we need really that everything must be linear. So to start with, the PDE should be linear. But there we can do the trick that we can linearize it. So we can look at a certain point, and the nonlinear problem, a linear problem. But for doing the scheme, it must be linear, otherwise we cannot do it. And not only linear, the coefficient could still depend on space and time. We don't have that. The coefficients must be really constant. So the FDM, finite difference method, must have constant coefficients. And that is not a problem for us. For the forward time central space, we assume that the alpha thermal diffusivity is constant. We have chosen a delta T or delta X, they are constant, so that is no problem for us. But there is a prerequisite which is usually a problem. That is periodic boundary conditions. So we must have some periodicity in the problem. Say internal machinery, that is not the problem, but for many problems it is. But there we simply assume what do we get when we have periodic boundary conditions. So it gives us some condition. It turns out that the conditions that we get from this analysis are useful even if we have non-periodic boundary conditions. But we cannot be sure. But it gives us some indication. And the other prerequisite that we usually have for finite difference method in our applications, that is an equidistant grid. If we would not have it, we would do a coordinate transformation such that in the transformed coordinate we would have an equidistant grid. So the delta x is simply constant, that is what it's saying. So that is, those are the prerequisites, and doing that I just mentioned that we can waive some of the prerequisites and still get useful information from this for Neumann stability analysis. So I've been using it, for example, for the compressible Navier-Stokes equations. And they are in general not periodic for the applications I've been considering, but still I got very useful conditions that proved valid for, say, for aerodynamic applications. We make here another assumption, that is, to simplify things a little bit, that we assume now a period. So we assume we need periodic boundary conditions, and we assume that the period is L equal to 1. And that means that we assume that U of xt is equal to U of x plus 1 t. Note that I write x, not just the boundaries. You can do it at any point. Usually you consider from 0 to 1, but this is valid everywhere. So if we have the period 1, then it just means this. And we shall actually consider this interval from 0 to 1. So that will be our interval. If you want to generalize it, that would be just an L as you like it, but the things are very similar. So the interval with the grid points are then xj, and that is j times delta x. And now I use the notation that we introduced already, from 0 to nj. So nj is the number of grid points in the interval 0, 1. And the grid spacing, delta x, is then, as the interval is 1, and we have nj intervals, nj plus 1 grid points, just like that. And the periodicity at the boundaries means, in that case, that u of x equal to 0 at any time t is equal to u of 1 t. So that is, you see here the period. So we apply simply this here at x equal to 0. And from that, we get already a condition for also our numerical solution that must fulfill this. Our numerical solution, this will be our u0, it will be approximated by u0, and this will be approximated by u and j. So this periodicity implies already, and give it a number, that the u0 at any time t is equal to the u and j at any time t. So that is the periodicity, and if we do the discretization, then it would mean, when we do the discretization, it would mean ujn equal to u0 unj n. So this would be for the discrete problem. This is the semi-discrete problem. So now let's start with the von Neumann stability analysis for the forward time centered space. First remark is, when we do the computation of anything in computation science, not CFD only, but whatever you like, we do not get what we think we get. We get something that the computer represents, that it can represent. So we get some floating point number, and thereby we have some rounding error involved. We have discussed it done an exercise on that in the first exercise. Here we look in particular at the forward time centered space scheme. So what I write here for that scheme is valid for all schemes. So we do not get what we think we get. We do not, for example, a numerical solution to Jn on the computer, but we get something different, and that is, we can write that in the following way: ujn, I call it tilde. And that is the solution that we want to get, our numerical solution, plus some rounding error. And I use a notation from the book by Fletcher, Tannehill, Anderson, epsilon jn. So where the epsilon jn is the rounding error. And xjt. So now we can insert that's what we get on the computer. We can insert that in the forward time-centered space scheme that we compute on the computer in reality. So let's see. So we insert now what we get on the computer into our forward time-centered space scheme. And that yields the following. So then we replace what we had there originally by the uj tilde. So that is what we have on the computer. And that uj, actually that is the ujn plus 1 tilde, that is then consisting of what we want, the exact finite difference solution at the new time level at the grid point xj, but we will also get some rounding error. The same is true for ujn. So there we will have some rounding error. Then on the right hand side we have the thermal diffusivity and the grid spacing squared. And then there's also there the uj plus 1n plus the epsilon. So everywhere for any value we want to compute, we have to add the rounding error. Ujn plus epsilon jn plus uj minus 1n plus epsilon j minus 1n. So, and then we see that if we have that, and we know that the exact finite difference solution satisfies our usual scheme, that is 17, then we get, we can argue, since the ujn satisfies the finite difference method of 17, we simply can subtract that, and then we get the same formula for the truncation error. So then also epsilon jn does satisfy the finite difference method. So then you get the following. That is 29. Epsilon j n plus 1. So we get the same formula that we have for the original scheme for our approximations of the solution of the heat equation. We get now the same formula for the rounding error. So that is then alpha x squared epsilon j plus 1 n minus 2 epsilon j n plus epsilon j minus 1n. Let's see. Okay. And the same is true for the boundary condition. Of course, if the boundary condition is satisfied for the uj, it is also satisfied for the uj tilde. That is the equivalence on the computer that we can do. So, as the u tilde at 0 is equal to the u tilde nj, that is what we require. was the boundary condition. Same is true then also for the U0 n njn. We get periodicity of epsilon n. So that means we get also the epsilon 0n is equal to epsilon nj n. So they are also pure. So then we have a problem where we have now actually nj values at our nj grid points from 1 to nj. We don't need the 0 because that is the same as at nj. So then we have nj numbers for a periodic problem, and then we can represent those numbers by Fourier modes. So it's a trigonometric interpolation that we can do. So write that one way. The nj numbers epsilon jn, j from 1 to nj, can be expressed as a finite sum of Fourier modes. The following way: epsilon jn is equal to the sum, start now from here by 0, to nj minus 1. Then we have the amplitudes epsilon l n, so they are then dependent on time, these amplitudes epsilon hat, and the modes are indicated by e to the I is the imaginary unit, 2 pi l xj. Where I is the square root of -1, so that is used here. I is the imaginary unit. K is equal to 2 pi L, that is called the wave number. You see it is appearing here, 2 pi L. The sum is over the natural numbers from L to nj minus 1, but the 2 pi L appearing here is the wave number. And it is good to know what the wavelength is with respect to the wave number, that is 2 pi divided by k. So in our case it simply is 1 over L. That is the wavelength. And the epsilon hat, as I said, is the amplitude. So, and we also introduce here a notation with a k, because later on we like more to write k here to work with the wave number instead of the L. So we say that the epsilon hat k is the same as what we have indicated here in the formula with the epsilon hat L. That is the amplitude of the wave with the wave number k equal to 2 pi L. So that is the connection here between k and L. So that means we can express the rounding error as a finite sum of Fourier modes. Now we could do all the following by doing these arguments, but remember what we are discussing here is equally true for uj itself, ujn. we can also express ujn in this form. It's just that we look at different things. Here we are looking at the rounding error, but if we look at ujn, we are looking at the numerical solution. So we can do both, and they are exactly the same. The difference will be that these amplitudes will be different. So we can expect those here for the rounding errors to be quite small. And for the numerical solution, uj, then it depends on the problem, what is their size. But the form will be exactly the same. So, and I want now to prefer this form with the ujn instead, because that will make it easier later on to do the derivation. But what we are doing now is essentially the analysis for the rounding error. But instead of doing it for the rounding error, we are doing it now for the numerical solution. So I'll write that. So similarly, ujn, j from 1 to nj can be expressed as a finite sum of the Fourier models. That is then the following. Ujn is equal to the sum. Everything is the same as we discussed for the rounding error, except that we have now the amplitude u hat ln e to the I 2 pi l xj. So the notation is the same. We just note that the amplitude where u hat, we also use the k here, is equal to u hat l is the amplitude of the wave with the wave number k 2 pi l for the numerical solution. Uj can maybe extract. Let's see, for the numerical solution, I can indicate it. Let's see, how can we do that? I write it in this form, because here it is for the amplitude of the wave with wave number for the rounding error, epsilon j, and here it is for the numerical solution. So I want to rather to use this form, because as I said, it will make it easier in the end to do the derivation of the stability condition. We could do it here also, but we'll take this one. So this is then and the term that is appearing here, 31, I give it a name, uk hat e to the I, and now we use here for this the k. So this here is k. That is equal to k. We use that. That is what we argued here. This is the weight number. E to the I k x j, that is called Fourier mode. So that is important. So we can express then, as you see here, our, that is what we said, our numerical solution as a finite sum of Fourier modes. In the same way, we argued here, we can also express the rounding error, epsilon jn, as a finite sum of Fourier modes. The only difference is the amplitudes here. So the mode form is the same. So now we make the following argument. Since the vectors, I use the following notation, e to the I k x. X is now a vector, so it should be, say, the capital, a boldface x. And it's meaning the following: e to the I k x0, and so on, to e to the I k x n j minus 1. So here we start with the x0, we go to nj minus 1, but remember the xnj is the same as the x0. In our case, the x0 would be 0, and the xnj would be 1. But this is an n vector, nj vector. So we have then the k, and take b as 2 pi l. And we take the l from 0 to nj minus 1. So then we have nj of those vectors. And it is elementary calculus, linear algebra, linear algebra, to show that these are linearly independent. So since these vectors are linearly independent, so then that means when we have this sum here, if we look at that, so then for the different x's, these we have it for all the uj, we will have then here the vector x, and the L will then determine one of these forms, and all of these are linear independent. So it is enough then to look just at one node. So that is the idea. Since they are linear independent, it is sufficient to study just one Fourier node. Because when they are linear independent, then the behavior will be the same for each of them. So that is then makes life easier. What we are going to study then is how does the numerical method, in our case the forward time centered space scheme, treat one of these Fourier modes. Will the Fourier modes be amplified when we insert them in the scheme, or will they be damped? That is the question. If they will be amplified, we can expect that the method will not be stable. If the modes will be damped, then we'll have a stable scheme. So that will be our test. To insert just one Fourier mode into the finite difference method and look whether the mode is amplified, unstable, or damped, stable. So that is what we want to do. So let us write the goal. So to investigate whether a Fourier mode is damped apply the finite difference method. And that means that the finite difference method is stable. So that means if we look at U, the solution, but if we look at the rounding errors, then the rounding errors will stay bounded. For epsilon, it means that the rounding errors stay bounded. For n to infinity. So that is what we want. Or if the Fourier mode is amplified by the finite difference method. That means, in that case, that the finite difference method is unstable. And for the rounding errors, it means if we apply what these arguments, then for a Fourier mode representing the rounding errors, it means that then the rounding errors increase beyond any bound. So to do this, we insert a Fourier mode that is 31 into the FDM. That is 17. We should remark for epsilon. We would insert it, I think it was into 28. I think that was our finite difference. Let's see if I'm right. No, yes, I'm right. I think the 29. So I think it was 29. Okay, so that is what we check. We have these Fourier modes, and we just plug them into the finite difference method. So here that would be, say, the UK hat n, actually, if we are picky, it would be then related to the time level n. So I just added an n here. Okay, so that will be what we are going to do tomorrow, to do that and find out that from this analysis we get a very simple condition for the Fourier modes to stay bounded. And when we have that, then we then we know up to which bound we can go and we can get a stable solution. Okay, so it'll get more concrete tomorrow, I promise.